Welcome everyone. I'm happy to conclude the session on trains. I hope you're not bored by it already. So we're going to talk about maybe a bit more concrete problem again. And the task we're looking at is how to predict the duration of disruptions. So in the two talks before, we heard that there's disruptions in the network that lead to delays and that also lead to, they make the dispatching problem harder. So we're trying to predict how long these disruptions take. The work was done by Wettstein, who's also in this research and innovation platform that you've seen before. My name is Gabriel Krummenacher. I'm working at Silke Engineering, and I'm also working in this lab. So we're going to talk about how to handle disruption in the SVV network, why they're interesting, how people deal with them at the moment. We're going to talk about machine learning with text data because that's the basis of our predictions, and also machine learning with sequence data because that's also the data is in this form. So we're going to look at generally how to deal with this, and then we're going to show you the model that we have and the model that we want to have in the future. But first, Beat is going to talk about what disruptions are.
Yeah. Hello and welcome to the first part of this presentation. You see on this slide the SVV productivity over the time in the case of a disruption. In the case of disruption, the productivity is not going down exactly at the moment of disruption, a little bit later. And it would be down until an incident team has fixed or repaired, temporarily repaired the problem, and some train can drive again. With delay still, but after a while, you see that on T5, then we have operation normal state. And in our case, we want to predict this time period, also the operation disruption time. This is our target we want to predict. On the next slide, you see a symbolical presentation about the information content over the time. At the time of the disruption between the first two red lines, you don't have a lot of information on, almost nothing. And we call this period the chaos phase. But we have to inform our customer about the message. Okay, normally there's still a simple message like, we have a problem, please stay in the train or something like that. But after a while, especially when the incident team is on the disruption place, they have more information. And between T3 or T4, it's possible to route our customers with buses or with other trains to another direction or to another possibility. And at the end, we know what it is. Also, the problem is solved, and we have a lot of information at the end. But the case is we have to make the prediction at the beginning. Best is before T1. Or after T2. This is the thing. When you have not a lot of information, then you want to make the prediction. Our target is to make a prediction about the disruption time. We have some features like the place where disruption is. It's quite different if it's somewhere in the main station of Zurich or in Bern, or it's somewhere outside like Langenthal or somewhere there. Same with the feature of time. It's a difference when it is in the rush hour in the morning or somewhere in the afternoon. The weekday and the weekend is not so critical if it's on another feature is the month. It's more the season, if it's in the winter time or it's in the summer, who have an impact to the disruption time. And also the type of the disruption. And there are a lot of other features. I will explain one more later. Today we use for that the most perfect computer for that. He used the brain of the dispatcher. With his experience, he makes the prediction. But in the future, we will do that with a neural network. You see that with symbolical circles and lines. And our prototype is also built with a neural network, with random forest data. And you use also similar public frameworks like the group before, like TensorFlow, Keras, Pandas, NumPy, and so on. And we can also use this very high-performance infrastructure with a DGX1 from NVIDIA with thousands of GPUs, and with also millions of data. But still, this is not enough to make a very accurate prediction. You need something more. And for that, it's good you go outside. You go outside to the field and make your hand dirty. Okay, it's not dirty. And I want to explain a case for that, what we find a very helpful feature. In this example, this is the region of Bern, and we have a problem, a disruption near Rübingen. In a case like that, an incident team has to go first to the place of the disruption. And not the incident itself, the leader of the incident team. And for that, he will go to this place with his car. And we can calculate the travel time from his base. It's based on the main station, near Güterbahnhof in Bern, to Rübingen. And we can use a Google Map web service for that. Now I'll show you just a small part of Python. The first line is we have to convert the Swiss coordinates to the world coordinates. It's quite simple. You can use for that Swiss topo. And the second part is to call the web service. You need the address of the incident team, Güterbahnhof in Bern, and the coordinates of the disruption place. Okay, this feature, the travel time, this is also included with traffics and all that. It's very helpful, but it's still not enough. You need more feature. And other feature comes from this business application, Alea. A train dispatcher can use this application in a case of a disruption. He has an overview about, you have heard all the numbers of trains and that, but we have about 300 to 400 disruptions per day. And he has an overview there where there are. On the next part, he has an overview about the cases, what it is, and you can select one line, and then you have detailed information about the case. This information are just plain text. They are unstructured text, but it has a lot of very important information about the disruption. And we have to transform this information to features for the neural network. Just like this. You see here an example like a switch problem. It's a chronological sequence of messages. And when you want to make the prediction, you have to transform these messages to features for the neural network, and then you can make the prediction for the duration. And this prediction time, the dispatcher can also use this for make the train dispatching, disposition of the trains. Perhaps we can connect it with the simulator later. And the train dispatcher can also communicate accurate time to the customer. But open is now how to transform this text information, these messages, to the feature for the neural network. And Gabriel will now explain how that works. And I switch off this warm socket.
Okay. Thanks. So we have all these messages about the disruption that are entered by people, and they say, okay, someone's going to look at the disruption. We've seen that this is the problem. We called someone else. It's going to be here in 15 minutes. Things like this. And our goal was to use this information that's contained in these text messages to build a predictor for how long it's going to take the team and the people that are working on resolving the disruption to resolve the disruption. And so for this, the setting is supervised text classification. As you all know, machine learning works by looking at training data in the past and then building a function or model that we can then use to apply to future data. So here's an example. Imagine you have a set of documents, of text documents, and you want to classify them into different types. So say, is the document a letter, a blog post, a news article, an email, things like that. And for this, you need training data, so you have a history of documents that we are usually called X and labels that we call Y, of pairs of documents and labels. We are interested in building this classifier, this function that maps documents from X to labels Y. And so this could be any machine learning model, support vector machine, random forest, and in our case, a deep neural network. We use some learning method to learn this classifier, be it stochastic gradient descent or some convex optimization method, and then we end up with our prediction function. We can now go look at documents we haven't seen before and use the function that we've learned and predict the class of this document. So we could now say, okay, our function predicts that this is a blog post, for instance. Now, there's one step more to be able to do this. Like Beat mentioned, we are dealing with text data. So we need to make them available in a form that we can use in these methods, feature vectors. So we need a function that takes a document and outputs a feature vector for that document that represents the document as a vector. As soon as we have this, we can then use our favorite machine learning method and train a classifier on these feature vectors and then use them to predict the category of the text document. Now there's some well-known ways to do this. So here's an example. Imagine you have these 3 documents. So now we're back in the train disruption problems. So for instance, there could be a document that says there's an incident in Bern, there's a document that says the team has been informed, and a document that says that the disruption is resolved. So this, as you can see, there's information in this text that somehow help estimate the time it will take to resolve the disruption. So we're trying to build features from these documents, and the most simple method to do this is just to count words. So this is called Bag of Words. It's done by building a dictionary of all the words that occur in all the documents. So you see them on the left most column, and we have all the terms. So if incident, burn, team, and so forth. And then for each document, we just count for each word how often it occurs. So we end up with these very sparse vectors that have mostly zeros and have ones at the places where for the word that's contained in this document. So that's one way to do it. A bit more advanced would be to use TF-IDF, which is also what we've used for this problem. So it works very similarly, but instead of counting the words or terms, we normalize them by the words in the document. So we get the frequency of words per document, and we also look at the frequency of the word overall. So we look at how often does it appear in other documents as well, and if it's a word that occurs a lot in many documents, we weight the term less. So TF-IDF basically gives you how frequent a word occurs divided by how frequent it occurs in all the documents. So words like in, for instance, have less importance because they probably occur in all the documents. Now back to our disruption time prediction problem. So this is a visualization of our case. So top right-hand side, you see the stream of messages coming into our system. So this is the messages that are entered by humans into the system. And on the left-hand top side, you see where they occur. So this is this location that we've talked about. So this is all the disruptions taking place in August 2016, I think, some days in August 2016. And then on the bottom, you see our machine learning model. So this is the weights, a visualization of the weights in our neural network. And you can see that the model is learning something because in the beginning, these weights were all random. And now some of the weights are more important than other weights. So there's structure in the model. And then on the bottom left, you see the accuracy improving over time. So the more data we see, the more of these messages we use to train our model, the better our predictions get. So as you've seen, and as we've said a lot, we have this sequence of text messages. So it's not just one text document that describes the disruption, but over time, more and more messages are entered. And we would like to be able to look at this sequence of messages until some time point t, and at that time point, given all the messages we've seen so far, predict the delay. So we have this sequence classification problem, and we also discretize the output into classes. So we have these 6 classes of disruption times. So 0 to 15 minutes, 15 minutes to half an hour, and so on, are classes that we use to predict how long it takes to resolve the disruption. So these are important from the business side. So these are basically the bounds on where it matters. It doesn't really matter if the disruption takes, it doesn't matter so much if it takes 5 or 6 hours, but it really matters if it takes 15 or 30 minutes. So we need machine learning for sequence data. So what we've used for this problem is a recurrent neural network, which is a deep neural network specifically for sequence data. So any sequence of data point being text, audio, other sensor measurements, time series, this is the model that's used in these kinds of problems. So since we have this sequence of messages, we also use this model. So what's a recurrent neural network? It's similar to, say, ordinary neural network, but we have this recurrence relation. So we have an input x, and that we multiply with some weight matrices. So W, U, and O are the matrices that we learn. And instead of just like having H as the output, we also take into account what happened before. So this would be the different time steps. So if you have T time steps, at each time step, we would input the new message, compute this hidden state, and then based on the state of the time step before and the state of our current time step, we would make a prediction. So that the importance is that we take into account what happened, like what messages have been seen, some representation of these messages that we've seen in the past, and not just the message that we see at the moment. So how does that look for our problem? So we get a message like the disruption has been resolved, something like this. We compute these TF-IDF feature vectors. We feed them into the first step of our recurrent neural network, and we get a prediction. And then the second message arrives. Someone went there, did something. He enters this as a message. We compute features and get a prediction, and so on and so forth, until the time where we say we're ready to make a prediction. So this is the model that we've built. So we have these messages over time. We add them to the neural network, this recurrent neural network, and we get an output. But as we've talked about, there's other features apart from these text messages that are also really important. So how long does it take? How long do we estimate that it will take the closest team that deals with this type of disruptions, this type of incidents? How long will it take them to reach the incident? Where is the incident? And what date and time is the incident happening? Things like this. And so they're global to the incident. They don't change over time. So we also add them, and then we get a final prediction. So this is basically our model. Now, what are the results? So we've tried this on data of 1 year for the German-speaking part of Switzerland, because then we don't have to deal with other languages, and built a small prototype in Python, and this is what we got. So we compare so you see accuracy, since we have these 6 classes. If you would randomly guess one of the classes, you will get 17% correct. If you're a bit smarter and look at the imbalance of classes and predict classes that occur often more, you get 20%. And then after 0 minutes, so only looking at this prediction of how long it will take a team to reach the incident, things like this, without any text messages, you already get 33% of the cases correct. And then the more messages you look at, the better the prediction gets. So after 5 minutes, you get 38%, after 10 minutes, 40%, and so on. 10 minutes is from, say, a dispatcher position it would be good if after 10 minutes we could say something. So this is somehow the target. After 10 minutes, we should be able to get a reasonable prediction. And then, I mean, if you wait for an hour, maybe it's not so useful anymore to have a prediction. And also, after an hour, a lot of these incidents have been resolved. So here we're also predicting incidents that we actually know that ended. So if you take this into account, obviously after an hour, since a lot of classes don't exist anymore, we can take this into account and would get even better. But what we're really interested in is after 10 minutes. So the performance we have after 10 minutes of looking at these messages. So this is the prototype that we have. There's a lot of things on how we want to improve this from a modeling perspective. So we've talked about this feature vectors for text data, and one problem with them is that they don't have a notion of word similarity, and also they don't have a notion of sentence structure. So there's in the first document it talks about an incident in Bern, and the third document talks about the disruption. So we know that those words are similar. They're talking about the same thing, but the way these features are constructed, this is not captured. So there's a completely different count for resolved and for incident. And also there's no sentence structure. So first I'm going to talk about how we plan to deal with the word similarity problem. So there's this thing I'm sure many of you know called word embeddings. So instead of just computing this feature vector for the whole document, you could compute the feature vector for one word. You would start with counting again. So instead of, you use the same dictionary as before. So we have this dictionary of words. And then instead of doing this for the whole document, we do it just for one word. So you get a vector that has 1, 1, and all the rest is 0. So the word incident would just be a vector where the first word is 1. We compute a function that embeds this into a dense feature vector. So there's many methods that can do this. A famous one is called word2vec that actively optimizes this embedding function to have words that occur in similar contexts to be close to each other. So we could use something like this to capture that incident and disruption are similar. We could also train the embedding directly on our target, so we would get an embedding that would get words close to each other to get maximal performance for the disruption time. We still have no sentence structure though. So the next step is dealing with this. So imagine you have 2 sentences like this, where in one document it says track not damaged, disruption resolved, and then the other one track damage, disruption not resolved. They have completely different meaning, but if we do just a bag of words kind of representation of the document, we would get exactly the same representation. So clearly there's some, that's a way that we could improve the model. So the goal would be to get a model that looks like this, where we would look at all the words in the documents one by one, embed them as word vectors, feed them into a sequence model as well. So we have an output for the sequence of these words, and then we would add these messages in a second recurrent neural network together with the global features and get a prediction. And as the last part, Beat is going to talk about our vision for the product.
Okay. With the talk already, we have millions of data from historical data from disruptions. We have timetables, very accurate from every signal position. But we trained our prototype only of historical data. And with that, you cannot impress our dispatcher. We need an application, a prototype, who can install in the operation center with live real-time data. And one part is to make an interface to the Alea base system to make a prediction from the real data. And then we have a lot of systems who make custom information. They will support with this information, and I think that would be about the next step, perhaps this year or next year, to make this prototype. Okay, thank you very much for this presentation, and we are ready for some questions.